Please give me some water. Can
you go ask Mom, please? You made it.
Thanks, Cat. It's so good to see you.
Kimber
Let's do
says
this thing.
she's here, but I don't see her.
We just had a short conversation, her and I, on the last link.
You and Kimber?
Yeah.
I will take you to the neighbors for pizza if you don't make a complete total pig of yourself.
Okay.
Tyler!
Come say hi to Janksy Cat. Come say hi to Janksy Cat.
There we go. There's Kimberly. Hey. Good. We're going to do some physics tonight.
You do that.
Yeah.
So awkward. Yeah.
I'm going to go eat dinner.
I'll be over in a bit.
Jesse, Vicky, and the in-laws
Here now.
pizza. 40 wings. You promise not to make a complete and total pig of yourself. We'll be going by the next. They're all their relatives. Dead sitting.
Janksy Cat, let's do this. It's
I'm
already
ready.
like 7:30.
I'm going to show you the test, and we'll go through it question by question, and we'll answer anything that you need answered.
Okay.
So let me share my screen with you.
Oh, yay. I can't wait.
Hey.
Wow, that's really good. Maybe if I turn my screen sideways, I can see it better.
Okay. Well, let's just talk through these. So the first one says, the first question, if you remember,
I can't read them.
I will read them to you, Orion. You'll need to go to another room if it's too loud.
This is a huge Charlie Foxtrot.
Okay, so we are going to go through each of these questions. The first one says you're answering based on your understanding of Newton's laws of motion. So it says, many automobile passengers have suffered neck injuries when struck by cars from behind. How does Newton's first law or the law of inertia apply here? Use complete sentences. Anybody got any ideas?
Well, inertia has to deal with mass, the mass of an object.
Okay.
So if there's a massive car behind this little car and it hits this huge car, or this little car, then the big car is going to hit the little car, and the people inside the little car are going to get knocked back because the car is moving forward and taking an object at rest, or at least at a constant motion, to a further stronger motion, which is knocking their heads back.
Okay. So what does Newton's first
And then I think I remember a question on there about how to like seat rests help with whiplash, and or a headrest. So if you have a headrest, that's going to be that thing that stops that sudden motion.
Right. So Newton's first law says an object in motion tends to stay in motion unless acted upon by an outside force. It also says an object at rest stays at rest unless acted upon by an outside unbalanced force. So the person's head, is it at rest or in motion before the car hits it, before the collision?
Well, is the car moving or is it
Stop. Let's assume that it's stopped at a stop sign.
Okay, if it stops, then the rest, or the neck or the head is at rest until it gets hit by the unbalanced force of the next car, which puts it into motion.
Okay, so it's going to stay at rest, right? So it's at rest, it's going to stay at rest. What happens is when that force hits the car, the head stays at rest, but the body and the car move forward. which makes your head move backwards. And then it reaches a physical limit because it's attached by your neck, right?
Yeah, sometimes.
And then it comes forward. And so that's where the injury comes from Newton's law.
Okay.
So the headrest applies an unbalanced force. So we add headrest to cars because so we add, your head is here, and it's going to stay there as the vehicle moves this way, but that headrest adds an unbalanced force to keep the head moving.
So it moves the head with the car.
Right. So that your head doesn't stay stationary. It applies an unbalanced force and keeps your head moving with the car as well.
All right. Okay.
Kimber, for some reason I can't hear you, but I'm assuming that you can still hear.
You muted her for some reason.
Well, she's not unmuting, but she's unmuted over here, so I don't know why she's still muted. I don't know if she muted herself or what.
All right.
Okay, so I guess, Kimber, just follow along. If you have questions, you can type them in the chat.
No, Keegan just grabbed my iPad and accidentally muted me, so I grabbed it back.
Okay, so any questions on that first question?
No.
Okay, so let's look back at the next part of that, which says, how does headrest help? So they apply that unbalanced force. Okay, the next question on there, any better, Logan and Kimber? Can you see that?
No, that screen just well.
I'm gonna take a picture and send it to you, Jenks, because it's terrible.
Okay,
It's
well, I'll read it to you.
Distorted beyond belief.
All right. Well, it says, suppose you place a ball in the middle of a wagon and then accelerate the wagon forward. Describe the motion of the ball relative or compared to the wagon, and relative or compared to the ground. So what would we say would happen to that ball?
It would go with the wagon, the direction the wagon's going, because the force is pulling it that way.
Much better.
Okay. So Kimber says the ball would move. The ball would move in the same direction as the wagon. Logan, do you agree or disagree?
Wait, so the wagon's at rest and then it starts to move?
Yes, it accelerates.
Then the ball's going to go in the opposite direction of the wagon, backwards.
Okay, so what you're saying, the wagon's at rest. What is the ball, at rest or in motion before the motion?
If they're both at rest, then they're both at rest.
Okay.
But once one's in motion, then the other one's going to be, once the wagon's in motion, then the ball's going to be in motion.
Okay, and when the ball's in motion, is it going in the same direction as the wagon?
No.
Or opposite?
Opposite.
Okay, so we're close. They are both at rest, but once the wagon starts moving, the ball has very few forces acting on it, and so it stays stationary. It's at rest. The wagon moves underneath it, but the ball stays at rest. It doesn't roll the other direction. It just stays stationary.
But because it's on the wagon, the friction of the ball is going, or the friction of the wagon is going to move the ball.
Very, very
So
little.
the ball's rolling.
Not enough for it to matter into an answer on a test.
Okay, so your next question on that is a bowling ball. A bowling ball is more massive, so it's going to cause more friction on that wagon and roll backwards when the wagon moves forward.
Okay, so the ball and bowling ball, it's the same ball in both questions. But so this is again Newton's first law. And a lot of people had their drawings correct in that the ball moves backwards and the wagon moves forward, except for the ball doesn't actually move backwards. It's staying stationary as the wagon rolls out from underneath it. I mean, it is going to physically roll as well, but it's staying placed.
But the ball is being put into motion this way. So the wagon's going this way.
Yes.
The ball's being pushed into motion this way. So let's say the ball falls off the wagon, and it's going to continue to roll the opposite direction because it was already in that motion.
Yes, but the ball is essentially, there are some friction situations, but the ball is essentially going to land on the same place where it started on the wagon. So that wagon's going to move, but yes, it's just going to roll. It's essentially going to fall in the exact same place.
So it's staying in the same place, but it is rolling.
Yes, it is rolling, but it's...
So you should say a soap-covered ball in on a dinner plate.
A what covered?
Like that. You should specify this question. So I don't get it wrong on the test and have to hang out with you at 6:45 on a Sunday night.
It's going to be resistant to changes in its motion. And the minimal amounts of physics are not enough motion to make it accelerate much. So it's essentially not going to move. Okay? Questions on that one?
Okay.
Okay, I'm going to share this part again. Okay, so these parts on Newton's second law where you're calculating, do you have questions on those?
No, I got...
Logan, questions?
No, calculations are easy. It's
right. Okay, so essentially just so in case
F equals ma.
Right, just in case anyone comes and watches this later, it is just net force is equal to mass times acceleration. And so you're just going to rearrange algebraically to determine the variable that you don't know. So in this first one, situation 1, it's going to be net force divided by mass is equal to acceleration. So 20 divided by 4, it's going to be 5 meters per second squared acceleration. On the second situation, net force is equal to mass times acceleration. 2 times 5 is going to be 10 newtons. And on the third situation, it's going to be net force divided by acceleration equals mass. And if you want the advanced score, you're just putting in those variables, F, M, and A, in whatever arrangement they need to be. Okay?
Gotcha. I feel like I did that right.
Yeah. The next situation is pretty similar. Basically, the only difference is that you're having to, in some cases, calculate a net force.
Well, the thing I muffed up on this was I didn't do like that.
Well, what just happened?
Amount of newtons left or this amount of newtons right. So I got this down.
Okay, so yeah, we have net forces and net forces in the same direction we add together, forces in opposite directions we subtract. Right, so this is being 12 newtons minus 7 newtons. It's going to give us 5 newtons. So we can have 5 newtons to the right. That's a key thing that a lot of people missed is we need acceleration and forces are vectors, so they have a direction, and we need to include that direction.
Oh, I forgot about that.
Yeah. So otherwise, I consider them to be naked. They're not well dressed. So you're missing some points for your not having your unit there. Okay.
Gotcha.
All right. So those are fairly similar. We're just F net is equal to ma, rearranging it, showing our work, and calculating the net force. Okay.
Gotcha.
Specific questions on the free body diagrams of the pig and the man.
I just don't understand free body diagrams.
Okay.
Is there one where you have to draw the earth?
Yes. There's the man, the pig, and the earth.
One I don't understand.
Man, pig, and earth. Okay, so Kimber, I do remember you struggled a little with free body diagrams, so let's go over those again. So some basic things that you should have is you should start with just a dot. Okay, so you should start with a single dot in the middle, and then you're drawing all of the forces as arrows away from that dot. And you're only drawing the forces acting on that object. You're not drawing any of the forces of that object acting on other things. Okay, so if we look at this man, the first free body diagram on the left, we're going to have a dot to represent the man. And what would some of the forces be?
Gravity pulling him down to the earth.
And the normal force pushing him up.
Mm-hmm.
Any ideas what some forces would be?
With some what?
Gravity, natural, and what's the other one we're forgetting?
What are some of the forces that would be acting on?
Oh,
Okay, there's going to be
the pig is pushing back on the man.
Yep, because the man's pushing on the pig is going to push back on the man. So we're going to have a downward force of gravity. We're going to have an upward force of the normal force. We're going to have a force arrow to the left on the applied force on the man from the pig. Is that it?
Yeah, because he's not. Oh, I guess if he's using applied force to step into the pig.
Okay, so we're close there.
Where's our dot? On his arm or like the center of his body or where?
And we consider the center of his mass as the place where we have our dot.
Okay.
So probably his belly.
Body. I mean, yeah. I mean,
okay, so his feet are pushing on that center of mass, so that's going to be another applied force to the right of the applied force that he's using to push the pig.
Yes. So he's pushing. If he's pushing on the ground, there's also a force acting on him, which is a frictional force. Okay, so anything that's up here in this problem that's underlined is that the pig does not move, and that we're considering frictional forces. So if the pig does not move, that also means the man does not move.
Right.
So he has to have completely balanced forces acting upon him. So right now we've got one force down, one force up, and one force to the left from the pig. We also need
an equal amount of frictional force needs to be applied to him.
Yes, and to the right.
From the ground.
Yes.
Okay.
So that's the key thing that lots of people missed is that frictional force that's there. Okay? And the pig's free body diagram is very similar to the man's, except for the friction and the applied force are in opposite directions.
Yes.
The man's pushing the pig to the right, but then friction is pushing him to the left, which is the opposite of the man. Okay? Then on the earth, what forces do we have on the earth, acting on the earth?
Well, the normal force and gravity.
Okay, so
the pig and human force, they're natural forces, technically.
So the ones that you are correct that there is the normal forces and there are gravitational forces. The only ones that I'm expecting you to have are gravitational forces in the upward direction. If you have the normal force from the pig and the normal force from the man downward, that's perfectly fine. But the one that you have to have is the gravitational force of the man pulling on the earth and the gravitational force of the pig pulling on the earth.
Okay, so what about the center of the earth pulling on the earth? Downward.
No, so our earth, just like the man, we put it at the center of the mass. The force on the earth is the center
Oh, okay, I get
that. And we consider any force applied to that man is applied to that dot.
Hello?
So any force we apply to that man, we draw on that dot for his free body diagram. The same is true for the earth. If we draw a dot for the earth, we draw all forces as if they're acting on that center of that dot.
Okay.
Okay. Okay, so the part that we struggled with as a class on this is identifying the third force pairs. Okay, but we've talked about some. So what would be some third force pairs?
Those are the ones where the two variables have to switch, right?
Say that a little louder.
Those are the ones where the two variables have to switch, right?
Right. So, like, the man, there's an applied force on the pig from the man. The third law pair of that is the applied force on the man by the pig.
All right.
That's one pair.
And you get the force pairs from two separate diagrams?
Yes.
Okay.
They always include two separate objects. They always have to be two separate objects. They can never be on one single object.
Okay.
So it's the man and the pig and the man. Same thing is true if we do the earth and the man and the earth. So the gravitational force on the man by the earth and the gravitational force on the earth by the man is another pair. They're two separate objects, opposite directions, but they're the same size. And then we have the pig as well. So the gravitational force on the pig by the earth and the gravitational force on the earth by the pig, they're on two separate free body diagrams, but they're in opposite directions, and we've switched our
Okay.
Okay? Does that help?
Okay.
Gotcha.
Yeah, I don't know. They're
tough.
I don't understand them, because when I think of like forces, I want to draw the arrow towards the point of like. And
So instead of drawing it towards the person, you're moving the tail of the, you're moving the arrow to the opposite side, and the tail is connecting to the dot. So you're always getting your forces in the appropriate directions when you do it, but you need to connect the tail and draw it from the center of the person.
Yeah, I'm just stupid.
No, you're not. So it's just some practice and some refining of how you do it. You're good at identifying the forces, but just drawing in the appropriate way is all you need to add. Okay?
Yep.
All right. And if you need more practice, let me know and we can look at it.
Okay.
So this one is the last question on here, the flatbed truck. He's colliding into a concrete barrier. The crate is not tied.
Oh, yeah.
And we use all three of Newton's laws to answer the statements for. Okay, so let's look at this first law of motion, the law of inertia. It says, describe what would happen to the crate not tied down at the moment the truck impacts the concrete barrier as it relates to the first law of motion. So Kim, how would you describe the motion of the crate just before the truck hits the barrier? Is it motion or is it inertia?
I said that the crate was moving.
Okay. So when the truck hits the barrier, Logan, are there any outside forces acting on the crate?
Friction.
And is that a big force or a little force?
It's going to be little.
It's going to be a very little force, right? So generally we can assume there's basically no forces acting on the crate.
Okay.
Okay, so what would happen to that crate?
It's going to fly forward.
I said it would fly forward.
And pretty much everybody got that correctly. Some of the reasons were incorrect, but it's going to move forward because an object in motion tends to stay in motion unless acted upon by an outside force. And there are no outside forces, or substantial ones, acting on that crate, and so it's going to continue to move forward. Okay? So you got an advanced score if you could say, highlight this part, an object in motion tends. So you could say, you know, the crate is in motion, and so it's going to be in that motion.
Hello?
Forces. Okay?
Gotcha.
So let's look at second law. This is basically another force equals mass times acceleration. It says if the truck is moving at 35 miles per hour, approximately 15 meters per second, when it collides with the barrier, it should have an acceleration of approximately 456 meters per second. If the truck has
and you just have to calculate that.
Yep, so we just do force. Net force is equal to mass times acceleration. We're given a mass, we're given an acceleration. Just calculate it. Okay? The second one, it says if the truck were moving double the speed and therefore most likely double the acceleration, how would the forces be different?
They're going to double.
Okay.
I said the object would then increase in its force because the mass would stay the same.
Okay, mass stays the same, our acceleration doubles, right? We double our acceleration, we double our force.
If anything in that equation, if any of the variables in the equation double.
Right.
Or no. So if, what's doubling? Acceleration?
Acceleration.
Okay, so if acceleration doubles, then the force is going to double. But if mass doubles, then the force is going to half.
Nope. It's still going to double because its force is equal to mass times acceleration. If we have 2m times a, it's still going to be twice as big as if we have m times 2a. It's all multiplication. There isn't any division in there.
Okay, okay.
So it doesn't matter if we double anything. If we make the truck twice as heavy or we make the acceleration twice as fast, we're still going to double the force.
Okay.
Okay? So again, you get an advanced score if you can say if this, then that. If we double the acceleration, then we double the force.
Okay.
And if you said if we double anything if we double the mass or the acceleration, we're going to double it. Okay. So this again is another third law. You're going to describe how third law of motion applies, especially the interaction of forces between the truck and the concrete barrier. So we need 2 free body diagrams, and a lot of people drew correct free body diagrams to the barrier and the truck, but nobody identified, very few people identified the third force pairs. So we can do that by circling them, the 2 parts of the free body diagrams, whatever we need to do to show those pairs.
Just identifying them?
Yeah, and very few people did. So that was an issue. But so basically we could have the force, the applied force on the barrier from the truck, and what's going to be equal and opposite to that.
The applied force on the truck by the barrier.
Yes. Okay, that's 1/3 law pair. And then you can just find another one, which can be the force of the crate on the truck and the force of the truck, the normal force back on the crate. It could be the truck on the earth and the earth on the truck for gravity.
Just the problem of identifying them?
Yeah.
Okay, sounds good.
Basically, you're identifying the force between the truck and the crate and the truck and the barrier, and then you're finding one other third law pair anywhere else. Okay?
All right.
And if you can, you can get
What?
and circling on your free diagrams. And if you say, put it in a sentence, it counts as a verbal diagram.
Okay.
So did you guys watch that video on Newton's first law?
With the inertia and the fat guy riding the bike?
Yeah.
Yes.
That was the area that we had the most trouble with on the test, so I made that video, and that's what I'd say if you haven't watched that, but it sounds like you both did. But anyone else that watches this video should make sure to watch that, because it will be the most helpful.
Right,
I can't remember who I watched it with.
Any other questions?
I'll probably think of some by Monday.
Nice mustache.
Yeah, looks
Okay.
very...
If you think of something else, let me know. If there's specific parts, like Kim, if you want more practice on free body diagrams, just let me know and I can get you some more practice and I can help you on those. But if there's any other situation to help with, let me know. To finalize getting ready for the test, the retake, just bring that document that was emailed. That says, here's the things I did wrong, here's the things I needed to work on, here's why I didn't do well, here's what the teacher can do to help me, and then just bring that signed, and you'll be good to go.
All right, sounds good.
Okay.
Okay.
All right. So I will see you.
I'm hanging up now.
Okay, goodbye.
Good night, James.